Hey y'all, what's up? It's Coach Hyde. Coming at you with your physics lesson for the day. What's your name?
Rowan.
Rowan, what are we going to be learning? What's my favorite thing to talk about?
Float.
Something that floats, right? So, I don't know why, but I love stuff that floats. I like being on a wakeboard that floats. I like being on a boat that floats. I just like floating, right? So, two kind of things, density and buoyancy. So, first we're going to kind of dive into density a little bit, and then we're going to dive into buoyancy after that. So first off, what is density? Right? What is it? Well, it's a measure of two things within matter. It's a property of matter. Everything has its own density. So you could figure out the density of something. If you didn't know what it was, you could identify it by this property. Now maybe you needed, some things are very similar, right? Like different types of trees might have very similar densities. So you might have to look at some other properties as well, but the density can get you there, right? So the first component of density is mass. Now mass is not weight. Weight is something very different. It includes your mass, right? But it also takes into gravity into effect. Whereas you might weigh something different on Earth than you would the moon, than you would on Jupiter, because gravity is different. But your mass will always be the same, because mass measures the amount of volume, or no, sorry, I'm not starting over, but mass measures the amount of matter inside something. So how many pieces of matter or atoms or whatever you want to kind of think of matter as, what is that? How much is in the object? And we're going to measure that with grams. All right. The other component to this is volume. So volume is how much space something occupies within space, essentially. So we have this area all around us, and we think of it as empty, but it's not. It's occupied. There's things there. You know, if you think about the void of outer space, where there's nothingness, right? It's just empty. There's no air, there's no gases, there's no invisible things we can't see, right? So volume is talking about how much space does a physical object or particle or wave or whatever occupy. We're going to measure that in one of two things. First, we can do something kind of more fluid-based, such as the liter, or we're going to do something kind of more solid, rigid object-based, such as the cubic meter. Now, the meter on its own, right, like for a meter stick, could not measure volume. You could only measure a length, right? So we would need three dimensions, length, height, width, to measure how much space it takes up in the three-dimensional universe that we are aware of or exist in, I guess you could say. So if we look at these two objects here, one is more dense than the other one. This is, we'll say that this is 1 centimeter by 1 centimeter by 1 centimeter. So this is 1 cubic centimeter. This is also 1 cubic centimeter. So these objects, even if they're different, they still occupy that same cubic centimeter of space in size. Well, so this is not actually a cubic centimeter. If you're curious to what a cubic centimeter actually would be, where's that? Right there, right? That is 1 cubic centimeter of space. This is most of the time our base unit. This is also equal to 1 milliliter of space. But it's not liquid, so we would say cubic centimeter, right? If you ever heard the doctors on the TV shows going, give them 1 cc of epinephrine or whatever, right? This is how much of the medicine they're given, right? That much volume. So, excuse me. If we're looking here, we got about 1, 2, 3, 4, 5, 6, 7, 8 pieces of matter within this 1 centimeter cubed, right? If we compare that to this one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It got a lot packed into the same space. So this one is going to be more dense. It's got more matter packed into the unit volume, the base unit volume, right? So, and obviously, it'll be more heavier as a result. So that's density in a nutshell. We're not talking too much today about calculating it. We'll get into that later, but density is just how packed together is the matter, right? how packed together. So this, let's say this is a particle. So matter could be kind of spread out, like this one, right? Those are pretty spread out. Or it could be completely packed full with these. So if I had an object that was 10 centimeters by 10 centimeters by 10 centimeters, and it was slapped full of cubic centimeters, it would look something like this. It is slapped full of those objects. And when we talk about density, we're not talking about the whole object, right? We're going to break it down kind of like reducing a fraction to how much matter is in the base unit. The more is packed into these, the more dense the whole object will be, right? So if I was to calculate the density, which we'll worry about that later, don't lose that, this would have the same density of this if they were both the same substance. Now if they were not the same substance, they would be very different. Or maybe a little bit different, but they would be different. Here, go this one. You got it?
Wait, give me one more.
Alright, so that brings us to buoyancy. We know things that are light float. We know wood floats. We know styrofoam floats. You know these things just by being alive. As long as you've been alive, you know that some things float than others do. But then I would ask you, how does this happen? Right? I'm not doing nothing. And I can take this, shake it up, and let it chill. And even though I shook it as hard as I could, we got a little magic happening. So, what controls if things float or not? Right? If we give this a little time, as you'll see as I start talking, you'll see them kind of separate. So, although it looks like there's 3 layers in here, there's 4 things. So what things will do is more dense things are on bottom. And these less dense things like wood, styrofoam, cork, these things we know that float, they're less dense. They'll be on top. So things that are less dense than water or less dense than a liquid will naturally float on top because they have less mass packed into a unit volume, right? So as we see here, we're like, well, this whole thing looks like water. So down here in the bottom, we have salt water, NaCl and water mixed together. Up here we have alcohol, 91% isopropyl alcohol. They look the same, but they have different densities. And these 2 types of beads in here, the blue and the white, probably some kind of polycarbonate plastic things, a little bit different with a little bit different densities. The blue one is more dense than the white one. So we end up with the less dense thing up top and the more dense thing down bottom. So we're going to be a little bit more accurate with that and how we describe it. And if you'll focus your attention to this image, we will talk about that now. So, buoyancy, right? Buoyancy is essentially a buoyant force created by the water underneath, and then, the gravity is going to be the force pulling down on an object from up above. But based on density, we can look at it this way. So the density of pure water, right, pure H2O, is 1.00 grams per mil, or you could reflect 1.00 grams per centimeter cubed. So an object that is above that, right? So an object that is 1.01 grams per centimeter cubed or bigger, right? It will sink. And we will say that this is negatively buoyant. An object that is less than 1, so an object that is less than that density of water, it will float. It is positively buoyant. But what about an object that has equal density as water. If it is equal to this number, then it is neutrally buoyant. So, why do you care about that, right? You're never going to need to know that. Well, if you're interested in scuba diving, it's a very important concept. So, when you're scuba diving, you want to make yourself, when you got your tank on, you got all that kind of stuff on, you got a tank full of air on the back, you're going to be positively buoyant. So you would have to spend all your energy swimming, keeping yourself under the water. So you're going to add weights, right? You're going to add weights so that your overall density, your overall matter is great enough so that you will become negatively buoyant. So now, great, you don't have to spend energy sinking to the bottom. Well, you don't want to go all the way to the bottom, right? If you go all the way to the bottom, you're going to get down there, you're going to kick up dust and silt and sand and all that stuff on the bottom, and you ain't going to be able to see nothing. So you just want to go down close to the bottom, or close to the object you're looking at, and stop. Well, in that case, you need to become neutrally buoyant. So you're not sinking or floating. So you'll fill up your little vest you'll have on with air that'll keep you neutrally buoyant and keep you at the level you want to be at. Fish have these things inside of them as well as swim bladders. They can fill up and let out air to help them kind of control where they're at. So, pretty cool stuff. What we got? Is this buoyancy? Okay, so, sorry, trying to think what we're going to next.
Daddy.
Huh? Come on, what? All right.
I want to do it just like you.
Okay. So, sorry, I honestly hadn't got this far in the video. I was starting over and get her some drink or something like that. But we made it. So we talked about density. We got into buoyancy. So a little bit about the dude who kind of claimed the buoyancy law, physical buoyancy law, whatever it's called, Archimedes Principle. So essentially, Archimedes was tasked with finding out the density of something he could not measure. Because it was a crown, it was all weird shaped, he couldn't measure it with a ruler, he couldn't calculate it. So one day the story was he sat in a bathtub. When he sat in a bathtub, the water overflowed. Then he shouted, "Eureka!" He ran down the street naked. Eureka means I've found it. And what he found was, he figured out that when you insert something in water, you displace that water. So that water and that object cannot occupy that same space. Just can't do it. So what happens? It pushes this water out of the way. And what he found was the amount of water that he pushed away is going to be the same exact mass of the object that he put in there. And he found out if you submerge an object all the way in the water and you collect and measure that water, that will be equal to the volume of that object as well. But you might have to push it all the way down. So this allowed him to figure out he didn't get beheaded. I don't know. We'll watch a YouTube video about it later. So, well, who cares, Coach Hyde? Let's see it. Let's see it happen.
Daddy, I want to start like you.
Okay, in a minute, baby. All right, so what I have here is a very, very high-tech device. It is a plastic Tupperware jug thing, a little peacock plastic thing that is hot glued in with a valve on it. The valve is open, and this should be empty, right? Now it's empty. All right, so I'm going to close the valve for right now. So what I have here is a tennis ball cut in half. Two very different sizes of the tennis ball. It's not cut directly in half. This side's smaller than this side. So both of them are going to float, hopefully, right? Which one's going to sit lower in the water? So I'm going to insert the small one first. Then I'm going to insert, this one should go to the black line if I calculated correctly. That one in next. As you can see, this one clearly sits lower in the water. That makes sense because it weighs more. All right, so it had to displace more water so that that water would equal the mass of the entire tennis ball. right? So the heavier the object is, the more water it needs to displace. And once it's displaced the equal amount of water that equals the weight of the object, it will float. If this tennis ball weighed more than the amount of water it pushed away, it would not float, it would sink. So that's how you could take something like steel ships and make them float. You just got to shape them so they push enough water out of the way where that, if you were to measure the mass of that water, then it would be equal to the weight of the ship. So before I continue, over here, we got a little lava lamp. Right now it is off. So what I'm going to do real quick is turn it on. All right? And I just wanted you to see it turn on so you can see what happens. And we'll get back to that here in shortly, where we throw temperature into the mix a little bit. But if I add weight to this, right, it's going to push more water out, right? It's going to sink further down. It's going to displace more water. So, well, it's cool, whatever, you know, right? Love it. It's pretty awesome. What I'm going to do now is I'm going to open up this peacock. Maybe if I don't break off my hot glue seal. All right, so now what I'm going to do is I'm going to collect the water displaced by this ball. I have not tried this yet, so if it don't work, I'm going to be very disappointed. But in we go. All right, so it's going to go in. It displaced the water. Now we're catching our overflow. The water level rose when I put the tennis ball in. That water is being forced out of the peacock here, and we are collecting it. So, any minute now. All right. Going a little bit slower than I thought, but it's still working. So we're collecting that water, and then we're going to come over here when it's done. All right. This thing is old school, right? I couldn't get it to balance it out perfectly level. I don't know if you could tell, but one of these is slightly higher than the others, but it is set up here to show balanced. But so if this side over here is heavier, right, it'll go this way. If that side over there is heavier, it'll go this way. So we've collected our mass. So the mass of that water we collected should be equal to the mass of the tennis ball. My only fear is this, is the tennis ball is made with fuzzy stuff around it. So that fuzzy stuff, I just thought about this right now, is going to absorb water. So, might be a little bit off, but you get the point. So, here is the water we collected. Here's our tennis ball. This guy's dripping water. So this is absorbed water, which has increased the mass of this tennis ball, which means my experiment's probably not gonna work. So I'm gonna put it on here. Yeah, so see, it made the tennis ball too heavy. If it was dry, if I would used something plastic that did not absorb water, and you'll do this in class with a couple things we got, it would have balanced out. And the mass of the water would have been equal to the mass of the tennis ball. But, so it didn't work. Oh well, life goes on. Not a big deal.
Dad.
Huh?
I want to get on there.
Okay. I'm about to show you something cool, all right?
Okay.
Now, we look at our what is these things called? Lava lamps. We can start to see a little bit of something happening here in the bottom. It is heating up. So, when we talk about density, right? When we talk about density, we need to take into account temperature. Because if we're looking at these things, right, maybe temperature don't affect it too much, but usually it does. So temperature does not measure how hot or cold it is. We use it to get an idea of how hot or cold it is, but really there's no such thing as cold. Cold is not a real thing. Cold is just an absence of heat or an absence of kinetic energy, right? But if we were to heat this up, kinetic energy is the vibrating motion or vibrating energy of these particles. So if we were to heat it up, they would start shaking faster and faster and faster. Now, I don't know about you, but if you have two things next to each other and they start vibrating faster and faster, right, they start spreading out because they can't stay close to each other. So they start spreading out. That means they're going to start to occupy more space as a whole, which means they're going to become less like this and more like this. And I don't mean the particles are going to disappear. I just mean that they'll become more spread out. So this means they're going to become less dense. So they will create a convection current. And I don't know that our lava lamp's going to heat up, but as that stuff in that lava lamp, whatever it's made out of, heats up, it kind of spreads out as the things start vibrating faster and kind of bouncing off each other a little bit. And they'll start to float. And then they'll cool off and sink. Heat up and float, cool off and sink. This is how winds on Earth are driven. This is how your fireplace in your house, can you build a fire in there and the smoke goes out the chimney? Because that smoke is air, it gets spread out, becomes less dense, and you don't just fill up your house with smoke. So that's how that works. So we got to take into account temperature. Temperatures will make things less dense, okay? Now, one more thing. Oh, Rowan, we need my lighter.
You need a lighter. I got it.
You got a lighter? No, a ruler or a lighter.
Oh, you talking about the lighter? Oh my God, that's gonna burn me. That's gonna burn me.
All right, this work.
No. It's gonna burn your glass. This is gonna burn your glass. It's gonna heat up. It's gonna get a lot of heat up. It's so many heat up.
All right, so what we have in here is there's a little bit of liquid in there. I don't know if you can tell. We're not going to pour that liquid out of this bottle. This is a flammable liquid that easily evaporates, some type of hexane. What we're going to do is show you that we can pour fluid just like you can pour a liquid, or any fluid. We can pour gas just like you would turn a liquid, because gases and liquid are fluids, both of them. So we tend to only think of being able to pour a liquid object. Well, most of the time, liquid objects are more dense than the air and all that kind of stuff, I guess all the time. But it's just like liquids, right, how you can separate liquids based on density, you can do the same with gases. So this is more dense than the air I'm breathing, right? The air around me is more dense than the air inside of this. And this happens to be flammable. So most of the time what we would think is if I take the top off and there's gas in here, it's just gonna fly out, right? But not this gas. This gas will stay in there. Now, because it evaporates easily, if I take the top off, it would all evaporate, right, as it gained energy and such. But right now, it's not. So, first step one, we gotta light the candles.
Daddy, I'm feeling that.
You about ready to watch this, Rowan?
Yeah. No. I know what it. I'm scared. It's gonna heat up. It's gonna heat up. It's gonna heat up. It's gonna heat
Oh,
up.
it blew out.
What does not working?
It's working. It's working.
Wait, how do you do that? What? I want to see. I want to see.
All right, watch this. So, I'm gonna come up here to the top of this ramp. Stay back, okay? I'm not gonna pour any liquid down it.
Daddy.
So, you can see the liquid is still in here. I did not pour any liquid down the ramp. Right? So, this air in here, this hexane air, is more dense than the air outside. Right? Dense things sink, they're negatively buoyant, and things that are less dense things float. So I can pour it down the ramp just like you would pour water. So try to get a little bit more to evaporate, and for your viewing pleasure, we will end by doing it one more time. You want to do it one more time?
Yeah.
You sure?
No.
No?
No.
Yes, sir?
Yes, sir.
You do want to do it? You don't want to see it on fire?
No.
All right, here we go. One more time. All right. Catch y'all later. Tell them bye, Ro.
Bye.
Bye.